For those who know where to look and how to make things happen, the world is a very rewarding place. And that's true not just in business, but in science as well. Here, there's water everywhere, and as you'll see, it's got a lot to offer. But I want to start with something that comes from somewhere about as far and as different from that as you can get. Take a look at this. It's a mineral called caliche, and it comes from the Atacama Desert in northern Chile. Caliche is valued because it contains something called sodium nitrate. But besides sodium nitrate, there are other things in caliche, such as salt and sand. So our first job is to separate what we want, the sodium nitrate, from what we don't want, the salt and sand, just as they do in Chile today. The sodium nitrate is used as a fertilizer. Now, I don't have to look very far for a hint on how to do it. Out there, things are kept separate from sand because they're dissolved in the sea. So I'll just add water, but in a laboratory.
First, I'll add generous amounts of caliche to hot water. The sodium nitrate and salt dissolve, but things like sand and clay don't. They remain in suspension. Now I'll pour the hot mixture into a filter paper held in a funnel. The paper removes the clay and sand, and what comes through is a solution containing dissolved sodium nitrate and salt. How can I separate the sodium nitrate from the salt? Well, if I cool this solution, the salt stays put. But sodium nitrate is different. Hot water can hold a lot of it in solution, but cold water only a little. So if I chill the solution, most of the sodium nitrate will crystallize out.
I'll just bank the ice up around it. Now it's a question of how long we have to wait. I can see some coming out now. That's beautiful.
Now, all I need do is to filter off those crystals, wash with a little ice-cold water and dry them. Here's the result. This purified sodium nitrate looks very different from the caliche from which it was first made.
This sodium nitrate came from a waterless desert. It had to, otherwise it would have been washed away by rain. But there are also rich pickings where water is everywhere. Along this coast, the cliffs take a beating from the sea, the rain and the onshore gales. Sometimes they collapse and hidden rocks meet the weather for the first time. What happens next depends on what's there. In Dorset, the cliff soil is often tarry, and there are pebbles of pyrite, fool's gold. At Lyme in 1908, a cliff collapsed and the exposed pyrite caught fire. The result was so spectacular that it was taken for a volcanic eruption. But what was really going on was chemistry, the weathering of pyrite. Here is some weathered pyrite from Lyme. These pale-coloured crystals are one of the products. They're melanterite, a sulfate of iron, and they dissolve in water. So I can separate them from the rock by adding water, filtering, and letting the solution evaporate. Here's the result. From these harmless-looking crystals of melanterite, I can make something much more disagreeable.
I've put some melanterite into a test tube with a cork in it. Through the cork runs a tube, whose other end dips into a little water in a second test tube. First, I'll heat the melanterite gently. It loses water as steam and turns white. Now I'll heat very strongly. The solid is starting to turn reddish brown. At the same time, fumes appear. The fumes and gas pass out through the tube and down into the water. Some dissolve or condense. Others just bubble through. You can see that the volume of liquid has grown. It's also fuming. The red-brown solid left in the heated tube is an oxide of iron. But the important product is the fuming liquid. I'll put it in a porcelain crucible and stick the crucible in a bath of hot sand. Evaporation reduces the volume. Fumes appear and it becomes quite viscous.
And this is the final product, an oily liquid with a boiling temperature of well over 200 degrees centigrade.
That liquid is concentrated sulfuric acid. It loves water, and when it gets some, it shows its appreciation by giving out lots of heat. Now, living things contain lots of water, so sulfuric acid gives them a terrible beating. It does the same to substances like sugar that living things contain.
Now it turns yellow at first. And then begins to darken. Now it looks quite treacly, but if I give it a stir, that'll start it turning into carbon. So there it is, a carbon volcano.
Concentrated sulfuric acid also provides an extreme way of tenderizing meat. It quickly reduces it to a hot sludge. This explains its popularity with acid bath murderers such as John George Haigh. Here's one of the drums in which he did the dirty work being taken into court. Haigh, an unsuccessful chemist, was hanged at Wandsworth in 1949.
What Haigh did was unnatural, but so in a sense is everything I've shown you. The things that I started with occur naturally, but the events that I brought about by using them usually do not. For example, my sodium nitrate came from the Atacama Desert, my sulfuric acid from something on the Dorset Cliffs. Normally, these two things would never meet. What happens when they do? I've put the sodium nitrate in the bowl of a retort. This is a piece of apparatus you see a lot of in horror films. Here's the sulfuric acid. I'll pour it into the body of the retort with the sodium nitrate. And remove the funnel. Then I'll put in the stopper. Next job is to heat it.
As usual, things take a while to get going, but when they do, we'll be rewarded with a new substance, nitric acid.
I can see some brown fumes above the liquid. What you're seeing here is an example of distillation.
Nitric acid is formed in the heated bowl. It boils, and the vapour rises and turns the corner into the cooler neck. There it condenses back to a liquid and runs down into the flask, which is kept cool by running water. The brown fumes are the gas nitrogen dioxide. It's formed by decomposition of a little of our nitric acid. The nitric acid is coloured because a little nitrogen dioxide is dissolved in it. Nitric acid acts aggressively towards most metals. I'll add it to some magnesium ribbon. Again, the brown fumes are nitrogen dioxide.
So now we have two reasons why that sodium nitrate in the Atacama Desert was once so important. It provided both fertilizer and the best way of manufacturing nitric acid. Sadly, those two reasons made it worth fighting for.
Here's South America. Two countries look completely landlocked: Bolivia and Paraguay. But that's not so. Paraguay has access to the Atlantic down the Parana River. Bolivia is the only landlocked nation on the American continent. Once, things were different. In those days, Bolivia included both this coastline and the town and port of Antofagasta. But the Atacama nitrate fields are here. And in 1879, Chile made war for them upon Peru and Bolivia. Chile won, and as a result, Bolivia lost both its coastline and access to the Pacific. Holes in the desert. This engraving was made 10 years after the war. It shows Chilean workers mining the nitrate deposits in the Atacama. Those deposits made Chile one of the wealthiest nations in South America.
What's so important about nitric acid that a chemical it was once made from can cause a war? Let's look at the reaction between nitric acid, sulfuric acid, and cotton.
These harmless-looking fibres are nitrocellulose. They're made by the reaction between a mixture of nitric and sulfuric acids and cotton pulp. And they don't look very different from cotton itself. But you'll see the difference when I put a match to them. Now let's see what's left. Absolutely nothing. Everything has turned into gas. Now you get even more sensational results if the reaction is carried out in a confined space. The Navy's battleships carried many tons of nitrocellulose in the form of cordite. In the heat of battle, a cordite flash fired shells at the enemy. But sometimes, the enemy's shells changed cordite's role from that of a propellant to a devastating explosive. At the Battle of Jutland, sights like this prompted Admiral Beattie's famous remark, "There seems to be something wrong with our bloody ships today."
When I saw the Invincible after the explosion, she went down, broken clean asunder in the midships. And when we steamed through the patch, there was the men on rafts, bravely cheering, and there was a smell of cordite, a smell of gas from shells, and also burnt bodies.
In what I've shown you, there's a particular kind of interest. I start with harmless-looking things like caliche, melanterite, and cotton. I end up with excitement, corrosive acids and explosives. Let me give you another example. When seawater evaporates, it leaves crystals. Most of them are sodium chloride, common salt, the stuff in the salt cellar on your dining room table. Now here's a harmless-looking material. What happens when I add sulfuric acid to it?
The sodium chloride is in the flask. The concentrated sulfuric acid is in the funnel. I'll run the acid in.
There's an immediate reaction and a gas is produced, hydrogen chloride. The gas bubbles through this bottle of concentrated sulfuric acid, which dries it. The tube carries the gas to the bottom of the jar. I've arranged things that way because hydrogen chloride is denser than air, so it fills the jar from the bottom up, pushing the air out. I'll keep the hydrogen chloride in with this greased white tile. Now let's look at the solubility of hydrogen chloride in water. If I invert a jar of air over water, the air stays put. What happens if I do the same with a jar of hydrogen chloride?
I slide off the tile and the water rushes in like a rocket. Hydrogen chloride is tremendously soluble in water.
A solution of hydrogen chloride in water is called hydrochloric acid. I've also made sulfuric acid and nitric acid. Why are these three substances all called acids? A proper answer to that question will have to wait. Here I want to show you how to recognize an acid when you find one. What you need is a purple dye called litmus and some pieces of limestone or chalk.
The litmus dissolves in water to give a deep bluish-purple solution. I'll add an acid to each boiling tube.
Hydrochloric acid, sulfuric acid, nitric acid. That's a nice red colour.
Acids turn litmus red. Now let's see the reaction with limestone. This time I've put the three acids in the boiling tubes. I'll add a piece of limestone to each one.
Hydrochloric acid, nitric acid, and sulfuric acid. Sulfuric acid reacts a lot more slowly than the other two.
That's because in sulfuric acid, limestone covers itself with a solid film of calcium sulfate. This film slows the reaction down. But in all three cases, you can see that gas bubbles are evolved. The gas is carbon dioxide. Acids react with chalk or limestone to give carbon dioxide.
There's one other important test for acids. Most of them react with the metals magnesium or zinc. I'll use magnesium and add it to hydrochloric acid.
Magnesium is used in spacecraft. There's more of it in orbit than any other metal. I'm using magnesium ribbon. In it goes. The gas is hydrogen. It's the least dense of all gases, so it goes vertically upwards. That means I can collect it if I hold another boiling tube upside down over the reaction.
Let's test it now. That's a nice pop.
A mixture of hydrogen and air burns with a squeaky pop. Most acids react with magnesium and form hydrogen. Because hydrogen is less dense than any other gas, it was once used to lift airships, but the practice couldn't survive incidents like this one.
Burst into flames. Wait, get it started. It's crashing, and it's crashing. It's crashing terrible. Oh my, get out of the way, please. It's bursting into flames, and it's falling on the mooring mast, and all the folks between us. This is terrible. This is the worst of the worst. Oh, it's running. Oh.
So a different gas, helium, is now used to lift airships.
What I've tried to show you is a way of making new things. You start with a pool of raw materials that you can pick up if you know where to look. Then you use a fancy kind of cookery to turn them or combinations of them into new and useful substances. Then, those new substances go back into the pool for more of the same treatment. The combinations are endless, and the result is something called the chemical industry, without which our way of life would collapse. But so far, there's no rationale to it. No reason, for instance, why you can't make copper by heating water and chalk. Now, in fact, there's a very good reason, and that's where the real science comes in. Reading about that will be your next job.